Great. Sorry about that delay there. I had a little technical difficulty getting this particular stream going. I am just going to get set up here for a moment. And I'll be right with you. There we go. Just going to make sure the chat's on. I'm going to share my no, it's give me 1 second here. Okay, so for our review tonight, I'd like to do a couple of things. One, first of all, to make sure that you know that you can use the chat over on the side, or you can text to 414-899-8269, and that'll get the work done as well. Going to get this screen shared here. Hold on one moment. There we go. Sorry, I was in Chrome and it wasn't working, but now we're good. Okay, you should see this now. You should see the data structures review slide. If you don't, let me know. What I'd like to do is I'm going to take you through a couple of things here. One is some of the things you should know, and a couple of things I want you to focus on in terms of our review. Now in class we went over quite a few of these, but I'd like to take you through some of these one more time. And that is, first of all, it's useful to draw out the Java Collection Framework organization. And it's a useful exercise so that you know the relationships in particular between the interfaces, the abstract classes, and the concrete classes. Remember that we have lists and queues and sets and maps as interfaces. They are not classes, so you can't create instances of them. So you'll want to know, in particular, what the concrete classes are that implement those different interfaces. And you're going to want to also study the fact that queues, while they are a subclass of lists, the concrete classes, that we have array queue and list queue, linked list versions of queues, that in the end, you'll want to know the relationship between the interfaces and their implementations. So if we talk about a pure queue, and this is important here, if we talk about a pure queue, we're talking about queues which only allow the interface of a pure queue, which is that you can offer something to put it on the queue, you can pull something to take it off the queue, and you can clear the queue, and you can ask for its size. But you can't put things at particular indexes or get things at particular indexes like you can with lists. So that's important to remember. And then likewise with maps, there are tree maps and hash maps. Okay. So in the case of lists, the queues and lists look a lot alike in that queues are kind of special types of lists in that, well, I only take things off of the front of the list, in other words, location 0, and I only put things on the end of the list. And so in that sense, they really do look like a list. And especially a linked list, those are nice fixed operations, aren't they? They're O of 1 operations. Array lists, on the other hand, taking things off of location 0, every time I pull it, that's going to be the least, the worst performance, because you have to move everything down. Now, typically queues aren't very long, so it's not a huge issue, but nonetheless, that is the case. Okay. Now, a circular queue is one where you could implement it in an array and simply run the index around that circular queue, where the head and the tail chase each other around that linked that list, that array. You'll want to know the basic implementations of all of these main data structures, as I've been telling you since the beginning here. And that is, you should be able to do add, remove, size, clear, and then as appropriate, get sub I and set sub I for array list and linked list. And that way you can always derive the performance from them. Because if that's the case, then you can sort of figure out, oh, well, boy, with array list, every time I take something out of a particular location, I have to move everything down that comes after it. Well, then the worst case scenario is when I take something out from location 0, the first one, because I have to move basically n-1 items down. So that's the worst case performance. On the other hand, taking something off the end of an array list is very fast, because I simply move the pointer down one and I'm done. So the other thing we want to know is what happens when we get exceptions for the indexes. Array lists can get index exceptions because I can't get anything past the end of the array, right? In other words, if there's n items in the array list, even if the array list implementation that has the array in it has a certain number in it, if I go beyond the number of items in it, if it's n items in it, then if I go beyond n-1, I'm going to have an exception. So you'll want to know the interface for the array list. Likewise, since they're both lists, linked list and array list have exactly the same interfaces, right? They're both just concrete implementations of the same list. However, the performance is slightly different, isn't it? Because when I insert something at the end of the list or the head of the list, it's O of 1 operations. When I search something, though, when I have to go to the ith item, if I want to go to the 6th item in a linked list, the only way to get out there is to go walking out there. However, in an array list, I can simply go to that location. So when we saw iterators, we saw that there was a way of improving the behavior of, in particular, linked lists, because with the iterators, I could remember where I last was, so I don't have to go out to the, if I want to get the second one and then the third one and then the fourth one, I don't have to keep walking all the way out to that item, but rather I can remember where I was and then go to the next one, remember where I was, then go to the next one. So the iterators will significantly improve the performance of my linked list. So with that in mind, if you had a linked list, then if you're thinking about how that works, we remember that you always have the head and the tail of that linked list. So things that work at the head and the tail tend to be pretty fast, right? Now, in a single linked list that does not hold the tail, to get to the end, you'd have to walk all the way out, right? If you only had the head. If you have the head and the tail, then it's pretty easy to deal with the very end or the very front. Okay. But if you have a list that only is a one-way list, in other words, it's a singly linked list, and it doesn't have the tail, then to get to the end of it, you'd have to walk all the way out until you get a null pointer. So that's important to know, that it isn't guaranteed to keep a pointer to the end. It just says sometimes we do that to make it pretty easy. So if you had a linked list that only had a head, you'd have to be able to get out to the end some way. So you can't assume that always exists. So think about how you deal with lists, linked lists versus arrays. Remember that linked lists have nodes, and they keep a pointer to the data, and they keep a pointer to the next item. And that each of those items has that same pattern of a pointer to the data and a pointer to the item, the next item. Whereas in arrays, you simply have the data at that location that's indexed, and I can move through the indexes. A lot of you had that incorrect in your exams and your quizzes. Make sure you remember the distinction between the implementation. Array list uses an array. Linked list uses a link of nodes, each pointing to that data. You'll want to know shallow versus deep copy. Remember that shallow copies only the attributes. So you can imagine that if you had an object, that you would simply make a copy of the values of each of those attributes. You aren't necessarily going all the way deep diving into them. You're simply copying them. So if one of the attributes is a pointer to another object, you're not actually copying that other object. You're simply making a copy of the pointer. So you have what's called an alias. In other words, you now have two names for the same object. You've made a copy of that pointer. That's very important. When you do a deep copy, if it's a pointer to another object, then you would make a copy of it. And you go, how do I know that it's a pointer versus just a scalar? Well, you know as the designer of that object that if you are implementing copy, then you would recursively say, oh, this is a pointer to another object. I'm going to recursively call copy on that object as well. I'm going to make a copy of that object versus simply copying the scalar value. So make sure you know the difference between shallow and deep copy. If you don't, make sure you email me later tonight or send me a text or something. But if you can imagine, if you are comfortable with the example we did in class several times having to do with the calendar, where a calendar had an array list of pointers to meeting items, then we said, well, a shallow copy of a calendar would simply be to copy the pointers to the array list of meetings. So there'd be two pointers to that same array list. So anytime you added a meeting or removed a meeting, both calendars would get copies of that. Would see that change. On the other hand, if you did a deep copy all the way down, not only would you have two calendars, but you'd have two array lists, and you'd have copies of all the meetings in that array list of meetings. So that if I changed any of the meetings in one, you wouldn't see them in the other place. But you might decide, in this domain, I copy my calendar, which is a collection of meetings. So I copy the calendar and the collection, but I don't copy the meetings. I only copy pointers to them because, well, we're all in the same meeting. So you'll remember that example. Oops. With binary trees, we spent a lot of time on binary trees, and I hope you're comfortable with those. What I want you to know the difference is, though, that there are binary trees that are ordered that we use for search, binary search trees, and there's a plain old binary tree that we saw, for example, with expressions where there's no particular ordering. There's simply the left subtree and the right subtree. But there's no implicit ordering to them, only that there's a left and a right. And so we saw, for example, with expression trees or family trees, that we could create trees that are not necessarily in any particular order, and that they are they're binary, but there's no particular ordering, and they're not necessarily balanced. You'll want to know how to do traversals of trees. So practice practice two different things. One is make sure that you can build a binary tree. Take some numbers, doesn't matter, or letters, and put them in kind of a random order. For example, take M, P, A, and T and build a binary tree by saying, does it get inserted in the left subtree or the right subtree? If the tree is null, in other words, if it's an empty tree, create a node, and that becomes the pointer to that subtree, and then copy it back up. Otherwise, if it's equal to the node, then it's already in there. Okay. Now, to traverse a tree, you'll want to remember how to do a pre-order, in-order, and post-order. A pre-order traversal of the tree says go all the way down the left, then go all the way, print out the root, or, hit the root, and then do the left, and then do the right. In order, I do the left, then the root, then the right. And post order, recursively, I do the left and the right, and then the root. And so the pre, in, and post order prefixes refer to whether the root comes before, in between, or after. That's, as long as you remember that, and you remember the recursive nature of it, super easy to do. Okay. For binary search trees, we have this additional interface, and the additional interface is the fact that it is a tree of comparable items. And they have to be comparable because we need to determine if it is down the left side, meaning things that are less than the root are down the left, things that are greater than the root are down to the right, and things that are equal to the root are the root itself. People often ask, they go, well, what if it's less than or equal to? No, it's either less than or equal to or greater than. And remember that comparable returns a minus if the target is less than, 0 if it's equal to, plus if it's greater than. So quick little review of comparable and how that works is important. So just take a quick look at that. And then a binary search tree has all comparable items in it. Otherwise, it wouldn't be able to decide whether to go down the left or the right. So when we insert things in binary trees, binary search trees, we insert smaller things to the left, greater things to the right, and if it's equal to, we don't do anything. Okay. With maps and sets, we saw this in the labs, and everybody did a pretty good job of that in the maps. A map is a set of key value pairs where the singularity is enforced on the key. So a map is a set of keys and their values where there's no duplicates in the keys. Remember, that's important. Okay. And so if we have a binary search tree, we can use that as an implementation of a map, because in binary trees, there's no duplicates, right? Otherwise, we wouldn't know which one was which. So it turns out that a binary search tree is a great implementation of a map, as is a hash map. But for a binary tree, it's a nice implementation, and it's very efficient for large maps, because what is the behavior, what is the performance of a binary search tree? It's O log 2 of n, right? So you'll want to make sure you know that. Then with binary trees, the next important thing was this notion of rotation. And that's where we attempted to get balanced trees all the time. So the idea behind rotations is that if we are out of balance on the left or the right by more than one, and you'll remember that the balance, that the height difference is calculated by saying the height of the right subtree, minus the height of the left subtree. If that's more than -1 or +1, then we can rotate it. Okay. Now, there are 4 situations, and it sounds more complicated than it is, but with the rotations, if it is a left out of balance, meaning the left subtree and then the left subtree of that is what causes it to be out of balance, then I can rotate it around the root, bringing the first child up to the root. The root becomes the right subtree, and then the left becomes the left subtree. If you can do if you are left out of balance, then you will do a right rotation, and that will bring it into balance. However, if it is left and then right subtree that causes it to be out of balance, in other words, if the height of the left subtree is out of balance because it is the left subtree and then the right subtree of that that's longer, then I have to first rotate that little right subtree around so that I have a left, and then I can do my full rotation around the root. And I think the book shows that pretty clearly. We did it in class a bunch of times, so you should be familiar with that. If you weren't in class, well, then maybe it's not so clear. But, and then the right and the right left out of balance is symmetrically exactly the same. It's just that if it's right out of balance, then I would rotate it to the left. And if it's left out of balance, then I have to first do that little rotate to the right down at the bottom, so I have all right out of balance, and then I can rotate it around the root. And I do that so that it's out of, so that I can get it back in balance. So it is useful to draw an out of balance tree and attempt to do a right rotation on it. So if you were to draw a tree that's out of balance on the left and then do a right rotation, try a couple of different examples, and that will do it for you. With hash tables, we have 2 important things to know. One is that there is the notion of open addressing and chained hash tables. Open addressing can handle at most n items. If the array, the hash table, is of size n, then it can handle at most n items. And that as it becomes fuller, there will be more collisions. And as we collide there, the only way we can insert new things is if they both hash to the same location, then I have to search for an empty spot to insert it. Or if I'm searching for something and they both hash to the same location, then I have to compare that location, and if it's not it, then I go to the next one, and the next one, and next one, and so on until I either hit null or until I've wrapped all the way around back to where I started. The problem with open addressing, while it's very efficient, is that A, I can only hold n items in it, and that its performance gets worse as the load factor starts to approach 1. So you need to be able to calculate load factors. Hint, hint. So make sure that you know that a load factor is the number of items in the hash table divided by the size or the number of slots in the actual hash table itself. So if the hash table is of size 11, meaning there are 11 slots in the hash table for an open addressing one, and there are 5 in there currently, then the load factor would be 5 over 11 for an open addressing. With chained hash tables, we handle collisions a little differently, don't we? If they both hash to the same location in a hash table, let's say it's of size 11, and they both hash to location 7, then at location 7, I create a linked list of items that all hash to that same location. So you can say that everything in that linked list, you know that they all have the hash value mod the size of the table that goes to that same location. So in both cases, both in open addressing and in the chained hash tables, that we want the hash function modded with the size of the hash table to result in hash values, indexes into that table, that are as evenly distributed as possible, right? In other words, we'd like the likelihood of getting a particular hash value to be exactly the same for anything that's stuck in there. If we don't, then we get a lot of collisions, and we wind up with the performance issue in the open addressing. We have to do a lot more probes. In the chained one, if they all hash to the same location, then I have to search down the chain looking to see if it's already in there, if I'm inserting it, or I have to look all the way down that chain to find it, resulting in a slightly degraded performance. Now, one of the things you want to know about the load factor of a chained hash table is that it can be more than 1, right? We saw that with an open addressing hash table, it can only go up to 1 because I can never hold more than n items, so it would never be more than n over n, or 1. But with a chained hash table, I can have multiple items at each location. So if my load factor were 4, that would imply that there's 4 times as many items in the hash table as there are slots in the hash table, or the size of the actual table itself. So that would imply that on average, there's 4 items at each location. In other words, there's a linked list of size 4 on average at each location. But as people have observed, you could have a worst case scenario, which is everything hashes to the same location, in which case you'd simply wind up with one long linked list. So for example, let's say our hash table were 11. So draw a little hash table with an array of size 11, a nice prime number, 0 to 10. Don't forget that things start at 0. 0 to 10. And if I had 44 items in it, that would imply that my load factor were 4, right? 44 divided by 11 equals 4. But what if I had a worst case scenario where everything hashed to 7? Then I'd have a linked list of length 44 where everything hashed to. So my performance wouldn't be that great, would it? So that's a worst case scenario. On average, though, there'd only be 4 items there. Okay. So if you were looking for something, you would find it usually half of the load factor, right? Because if in a chained hash table, if I had a load factor of 3, that would imply that on average there's 3 items at each location. And that if I were looking down that list, I'd find it in 3 divided by 2, halfway down, or about 1.5. So let's call it 2 comparisons is how often I would find something. So that's pretty good performance, right? Let's see, what else would be important to know? Make sure that you can do the basic implementations of array list for both add and remove. You should be able to write the add method for array list, where every time I add something at the end, I'm increasing the size, but I'm not necessarily increasing the size of the array that stuff is kept in until I get to the end of that array, and then I have to double it and reallocate it. If I remove something from an array, though, I don't have to necessarily shrink the array down. I just remove something. But when I remove something at a particular index, I have to move all the items that follow it down by 1, right? Size decreases by 1. And if I remove something from the middle of the array, then I have to move everything that was after it down by 1 until I get to the end of the array. So the worst case scenario would be if I remove something from location 0, because I have to move all of the other ones down. Best case scenario, I'm removing the one from the end. So you should know how to do remove. You should know, let's see, did we talk about traversal of trees? We talked about in order, pre-order, and post-order. You should be able to count all the items in a tree. So remember, there's 2 base cases. It's all recursion, right? Just always recursion. 2 base cases. If the tree is empty, in other words, if the pointer to the tree is null, size is 0. Otherwise, it's 1, which is the root, because it's not null. There's 1 plus the size of, recursively, the left subtree, and plus the size of the right subtree. Now remember, if those are null, well, they'll return 0, right? So you're okay. So if you just had a single node with 2 nulls hanging off of it, it would be 1 plus 0 plus 0. Otherwise, it would be size of that subtree and the size of the other subtree. It could be 0, or it could be whatever's below it. And so make sure that you can figure out the size of a tree recursively. Also, that you know how to value, how you can establish the height of a tree. The height of a tree is, if it's null, the height is 0. If the pointer to the tree is not null, it's 1 plus whatever is greater, the height of the left subtree or the height of the right subtree, recursively, right? Okay, just think recursion all the time. We talked about pure queue interface and the stack interface. Remember that those are very special data structures that are enforcing order of insertion, right? A queue is first in, first out, FIFO we call it sometimes, right? And that you are allowed to you're not allowed to deal with anything in between. So while an array list is a handy implementation of it, the problem is that, first of all, we can index things that are inside of it. And second of all, it's not very efficient because by definition, you're always taking off the front of the array list, right? When you pull a queue, you're always taking off location 0 on that array list, which means that you're always going to get worst case performance there. So the best choice for a queue implementation is a linked list, because it's O of 1 implementation when adding and removing things from that list. Oh, one other thing about hash tables. I think I just mentioned it, but one, you should be able to, of course, calculate the load factor. Number of items, total number of items in the table divided by the size of the array that's used to keep the pointers. In open addressing, the load factor can never go more than 1. Chained, it can go up more than that, but you're dividing it by the number of slots in the actual hash table. But remember that arrays are always 0 to n minus 1. So if you're size 11, your index, or size 17, for example, your index is going to range from 0 to 16. Let's see. Oh, let's see. For a map, remember that maps are collections of key value pairs, but that the membership is enforced only on the key. In other words, I can't have any duplicate keys, but I could have duplicate values, but I can't have duplicate keys. So it's just like in a dictionary. If I don't have any duplicate words, I can have multiple definitions for the same word, in other words, multiple values, but I only have one word in there. Likewise, and that's for a map of key value pairs. So you can imagine how that works in both a tree map and a hash map. Tree map, we know that we never have any duplicates in there. It's either equal to the root, or it's less than, or it's greater than. And then with hash maps, we know that there are no duplicates in there either. Now, to traverse a hash map, if I were to write an iterator for a hash map, how would you do that? We did that in class the one day. And basically, you have two levels of iteration, right? If you're doing open addressing, that's pretty easy. You just go down the array. It's whatever's in that array that's not null. Draw that picture in your mind, and you imagine an array with they're either null entries or there's the entry of the item that's in there. If it's completely full, there are no null entries. So you just go through the entire array. If it's not null, let's say you were printing everything in the array, in the hash map. Then in that hash table, you would, for open addressing, you would simply go down the array, and if it's not null, you would print it out. But with the chained one, which is the more common one, with the chained one, for every entry that's not null, you have to walk all the way down that list. Now, it's just a single link list because that's very efficient. But if it's not null in the entry, then I call the iterator on that list and I say, print out everything in that list. Then go to the next slot in the array. If it's not null, print out everything in that list, and so on until you get all the way to the end of the array. So you should be able to draw a picture of a chained hash table with n items in it. Doesn't matter what number it is. Let's say it's 5, 0 to 4. And imagine there's a chain of entries off of some of them. And some of the entries in that array of 0 to 4 might be null. So if you were going to iterate over that hash map, you're going to start at 0. If that entry is not null, then you're going to walk down that list, go to the next one. If it's not null, walk down that list. If it is null, you just move on to the next one. Okay. When you typically, when we initialize a hash map that's chained, a hash table that's chained, we set all the entries to null. And it's only when we insert things and we find that there's a null entry in there that we then create a linked list to start putting things in. I think we went through that in class in quite a bit of detail. Then finally, we went through different examples of how to pick the appropriate data structure. And so if I said, well, I've got, let's say I have people showing up at a ticket counter at an airport, as we observed in class one day, we thought, well, that's a good queue. So that would be the interface that we're dealing with. That's the behavior we want. We want it to look like a queue. Then we can say, oh, well, it's a list queue, for example, and that would be the actual implementation. So we could either use an array list or a linked list as our, because of the way queues are handled in Java, right? Queues are subclasses of lists. They implement the queue interface, but they can either be an array list queue or a linked list queue. Likewise with a map, we could say, oh, well, a dictionary of words, that's a great map. It maps the word to the definition. But we want to choose whether it should be a tree map or a hash map. Now, in the case of strings, we might say, well, let's do a tree map. If we wanted to just print things out in alphabetical order, a tree map is going to be a better implementation than a hash map, because a hash map will not print things out in alphabetical order. It will print it out in the order in which they are hashed, their hash values, and the order in which they were inserted, right? Because each chain of hashes will be the order in which they were inserted. If you were, what would be another good example? If you were going to keep a set of barcodes for different items in a warehouse, you could do it several different ways. You could say, well, it's really sort of a map of barcode item description. Or if the barcodes had a small enough scalar value, you might simply use that barcode as an index into an array list. So that would be faster, because I wouldn't have to hash the barcode each time. I could say, let's say the barcode ran between 0 and 100. Well, there's no point in hashing it. I could just use that as an index into an array list, right? It's still a list of items. I'd probably just use an array list and use the barcode as an index into it. You wouldn't want to use a linked list, because you'd have to walk all the way down the list each time to get to the nth item, right? Think about that for a minute. Let's say I said, oh, well, here's the barcode on some bottles. I don't know, there's some chemical, and the product code ranges between 0 and 99. You could have a list 99 long, and you'd say, oh, give me item number 21, and it would go get it. Well, if it's an array list, that's going to be really fast. If it were a linked list, it would have to walk down 21 items. But it would probably not be worth having a hash map or a tree map of it. That's a lot of overhead when you're only going to have 100 of them. So those are the kind of design decisions we'd want you to think about. Let's see. So far, I haven't had any questions. So I'm assuming that this is all making sense. I think if you know the things that we've talked about, you should be pretty confident going into the test tomorrow. Remember that you can have one 8.5 by 11 sheet of notes. You're going to need a pen or pencil. Pen's kind of a strong commitment. You might want to think about a pencil. I'll bring some extra pencils. And make sure that when you're doing your work that show me all your work. So that if I look at it and I go, well, okay, I can kind of see where you're going with this, you're almost there, then it's better off than if you simply write down a single answer. Okay. I think that's about it, if there aren't any questions. We're going to be there from 11 to 1 tomorrow. And I'm just going to quick check the location one more time. hate to have it change. Give me 2 seconds. 2852 is in 362, S362. That's where we usually meet from 11 a.m. to 1 p.m. It's over lunch. That's important to me, at least. So bring a Snickers bar or something equivalent. I'll have a few extra pencils. We're section 11. And I look forward to seeing you tomorrow and wrapping up a great semester, quarter, sorry. I never get that right. If there aren't any other questions, then we're going to wrap it up here at 9 o'clock. Any questions? Get a good night's rest. The rest is the most important. Drink some water so you sleep well, and we'll see you tomorrow. Good night.